Hello, I'm glad to present a work related to investigation of one novel method for operator inclusion problem in Banach Spaces. The work was performed by Kyiv University team with support of Ministry of Education and National Academy of Sciences of Ukraine. Here you see our general problem setting. So E is a Banach space, A is a multi-valued operator, B is a single-valued operator, and here you see the operator inclusion problem formulation. A lot of problem can be formulated in such a way. One prominent example is saddle point problem. As you see it here, we use normal cons for operator A, and operator B consists of gradients of function. Also, matrix games, constraint optimization, problem structural minimization, and some of machine learning problems can be formulated as minimax problem, and as a result as operator inclusion problem also. To get our theoretical results, we need some facts from Banach spaces geometry. For at least we need convexity, or to be specific, we need two uniformly convexity as defined here, and we need uniformly smoothness, again as defined here. Example of spaces with such properties are well-known spaces LP with P from 1 to 2. We use such generalization as normalized duality mapping, as you see it here. In case of smooth E, it becomes simply gradient of square norm. And for well-known spaces, it can be written in closed form, as you see here. Also, we use another generalization, which is called Albert functional, as you see it here. Actually, if E will be a Hilbert space, then it becomes square norm of difference x minus y. And for this functional, we have the next inequality, which is important for our algorithm constant mu, which will be used for restrictions on hyperparameters. And again, for well-known space, mu can be easily calculated, and you can notice that for L2, mu will become 1 because this functional will become simply norm x minus 1. X minus y. Here we see again our settings and assumptions which we need to get our main results. So A should be a maximal monotone operator, B should be a monotone and Lipschitz continuous operator, and solution set should be non-empty. If we recall the form of resolvent for maximal monotone operator, then our operator inclusion problem can be reformulated as fixed point problem. As you see here, it quite well-known form, and a lot of algorithmic ideas can be derived from such formulation. Here you see state of art about algorithms themselves. So, for example, we can see this algorithm, but it's quite well known, but it requires B to be inversely strongly monotone. So it's quite restrictive settings. Another example of algorithm does not require such strict properties, but you see we need actually two operator calculations on each step, also to this J inverse J, and one resolvent calculation. And the third is proposed algorithm, which we investigate in this work, and you see it requires only one resolvent calculation and only one operator calculation, because this value, of course, will be reused from previous step. So our main algorithmic results, you see here non-adaptive variant. I mean that step size lambda should be chosen and fixed from such interval, and you see we need to know both mu and Lipschitz constant L in advance. Here is an adaptive variant of algorithm. We do not need to know Lipschitz constant in advance here, because it's quite hard to find the Lipschitz constant for some complex problems, and it can be impossible. So as a result, often we need to simply guess this step size. And in such settings, we do not use Lipschitz constant. We use this substep 3, where we recalculate our lambda if needed. You can notice that actually this recalculation does not require extra calculations of B, because we reuse already calculated values. So this algorithm also requires only one resolvent and one B calculation. Again, Bx n minus 1 is calculated not on previous step. So here you see our main theoretical results. It's a theorem 1, which heavily uses inequality, which is presented in lemma 1, and also it uses above mentioned properties of Banach spaces. So you see that if E is 2 uniformly convex, uniformly smooth, A maximal monotone, B monotone Lipschitz continuous, solution set is non-empty, and also normalized duality mapping is sequentially weakly continuous. You see this red parts, we have a hope to lift these requirements, because now they're used in our proofs, but we have hope that they can be skipped maybe in some way. And if all this stands, then sequence xn generated by algorithm 1 or algorithm 2 weakly converges to some point z in our solution set. So it's our main theoretical result. Also some simplified setting for sub-problems. For example, for equation with monotone operator, algorithm becomes this algorithm 3. So we have no resolvent here, and everything is all other is the same as in algorithm 2. For convex minimization, for unconstrained convex minimization, we can formulate it as algorithm 4. And for variational inequality setting, which is useful because, again, a lot of problems can be formulated as variational inequalities, we can also formulate our algorithm. Resolvent becomes projection, as you see it here, and algorithm becomes algorithm 5, which have quite a well-known form and was introduced in earlier works. Of course, all our results hold for such variant also. Here we have some numerical experiment with a widely used test problem. As you see here you see operator B, and our constraints are intersection of cube and hyperplane. So it's the set where resolvent or projection can be calculated. And also this problem has a single and known in advance solution, so we can compare our solution to this. And we compare our algorithm to one of well-known algorithms, which is called extrapolation from the past. Here you see timings for different error size, and you see that all algorithms performed quite well, and algorithm 5, which is most advanced variant of proposed algorithm, performs slightly better than other ones. Here is the same comparison in terms of iterations. Again, you see that all algorithms performed well on this test problem, and adaptive version of algorithm 5 slightly outperforms adaptive version of extrapolation from the past. So here you see some selected references related to such algorithms, constructs, and so on and so forth. And thank you for your attention.